Okay, so this is only for the in-person classes. Again, the online classes are not doing any of the ACS exam requirements. General consensus right now seems to be leaning towards option 2, which means it only has the chance of bettering your grade. It doesn't have the chance of hurting your grade. If you don't do well on the ACS exam, it drops. That's funny because actually the reason we are putting it in the unit test was to incentivize you to come and do it. But this can actually de-incentivize a student. Don't come, you get a 0 and it drops. That doesn't, and we need the data for research. So that's kind of not the right incentive. Thank you for coming. But again, like it literally cannot hurt you. I say this to organic students all the time. We have an organic professor who doesn't require you to take the final exam if you're happy with your grade, because his exams are not cumulative. So one of your lowest exam scores drops no matter what. And if that's the final, right? It's just that last chapter. So a lot of students have an A in his class before they get to the last exam, which is not a cumulative exam, and they say, I'm not going to go take it. I get off easy. I'm like, why? What would hurt about taking it? Well, you don't do well on it, and it drops? Congratulations, you just got that learning experience. So if we really do go with option 2, you should just come and take it, because now it really cannot hurt you. It can only help you. If we put it in option 1, that means it could increase your homework category score. It could decrease your homework category score. It could keep you level. But option 2, it doesn't impact your grade, or it improves your grade.
Like you said, some people might not even show up. Won't even affect your grade. But I think the people who do show up, I'm going to take it more serious. It's joining my test grade, so I think you can get better data.
Okay.
Well, didn't you say that it was kind of like a good way to review for going into the final?
It's absolutely a great way to review for the final. You guys might realize we don't have a lot of review materials on Canvas. There is no practice final exam, much like there wasn't a practice midterm exam. I had a student email me last night. I haven't gotten back to them yet, but they asked for like a study guide of what will be on the final exam. And I've actually asked for this before from the course lead, and his response is, you have all the learning objectives from all of the units. That's your study guide. And I might actually take the learning objectives that I've been writing this semester and summarize them into their main points and try to create that learning objectives for you, knowing that that is actually more summarized and not specific, more general rather than individual ideas that you might see. But it would give you an idea of what types of questions to go tackle. I believe the STEM Center is going to be hosting a final exam review. They have an old version of an old exam, and so they have questions that they can take you through to review for the final exam as well. But the ACS exam is a great opportunity to come in and try your hand at a lot of the concepts that you've been seeing all semester long. So it can't hurt you. It's only a way to prepare better for the final exam, and it can even improve your score in the unit test category. But it is a challenge, 40 questions, 50 minutes. So put your best foot forward and go for it. I want to check back in halfway through class and see if we all still agree on that. All right. I mentioned at the end of our last class that I wanted to show you guys some cool videos, because I have these images in my head that don't always just translate when I'm talking. So this is a video of the triple point of water. You guys see some solid water, and you also see liquid water. That's because ice water was put into a vacuum chamber. What we're doing right now is decreasing the pressure in the vacuum chamber. So we've got solid, gas, liquid. We've got this pressure along the y-axis, temperature along the x-axis. We've got ice water, so we know we're sitting somewhere around 0 degrees C. And we're going from normal pressure down. Here's our normal pressure where I've got a solid and a liquid together, but as I decrease the pressure, I'm coming into that triple point. So you'll notice the water is boiling. It's also freezing. Do you see the ice sheet that's kind of forming on the surface here? You guys know what gas under an ice sheet looks like. That's exactly what that looks like. The water is boiling and freezing, condensing and melting all at the same time. Water is existing as all three phases. So this is like where our lines in the sand really butt up against nature's capacity to do some cool stuff. You don't have to say that water exists at one phase at a time, or that it even just transitions between phases. It can sit as all three phases. It can experience all of those different types of interactions. And here's another video. I'm going to let this guy kind of speak for himself.
Right before it reaches its supercritical point. The most fascinating part about watching a liquid turn supercritical for me is that before the supercritical point, there's obviously a liquid below with a gas above, separated by a line or a meniscus. But once it turns supercritical, that line just kind of fades away and it becomes one state, a supercritical fluid. But this gave me an idea and raised a question in my mind. If the line just kind of goes away, then what would happen if there was a boat floating on the surface of the liquid right when it turns supercritical? What happens to the boat? Does it just stay right where it was floating before? Or would it now float to the top since the whole tank is now filled? Or would it sink to the bottom because there's no layer of liquid to float on? Well, today I'm going to be testing this out by actually floating a small styrofoam boat in liquid CO2 and then heating it to its supercritical point. In order to do this, I have to contain a lot of pressure. The supercritical point of CO2 is at 73 atmospheres, which means I need to contain over 1,000 pounds per square inch in my vessel. So to do that, I'm going to be using this vessel here. It has two thick pieces of acrylic windows, and I can bolt these together over the body that has a valve and a pressure gauge right here. This tank has been tested to over twice the pressure that I'm going to get to today, but it still makes me a little nervous using it getting to this high of a pressure. So to start off, we need some CO2. When it's solid, we call this dry ice. So I'll just grab some chunks of dry ice and put it in the vessel. Now I'll tighten these bolts and then close the valve. As soon as the pressure increases, the dry ice stops turning from a solid directly into a gas. Oh, there it goes. But it can now turn into a liquid. So now we've got liquid CO2 in here. If I release the pressure, it freezes into solid CO2 again. Okay, so now let's do this for real. Let's put in our dry ice, and I'm going to add this half sphere of styrofoam to act as our boat floating.
I want to pause that for a second and point out, he mentioned the pressure was increasing. Why is the pressure increasing as the dry ice sublimes? There's very little gas inside of that chamber, and now the solid is subliming into a gas. That's increasing moles of gas, which has a directly proportional impact on pressure. Increasing the amount of gas molecules increases the amount of pressure in the system. So that dry ice is both warming up. Now at typical pressure, which would be about down here, 1 atmosphere, dry ice will move from a solid to a gas directly. As it's warming up, it's producing more gas, which means it's also producing more pressure. So now our temperature is not just moving horizontally with increasing temperature, it's starting to move diagonally with increasing pressure and temperature. So we get to this phase where his solid dry ice begins to melt. We're moving along that phase diagram.
Let's put our little boat in.
To see different phase changes.
Close it up. Okay, the styrofoam is very squished, but it is floating. Okay, now I'm heating it up. See if we can get to supercritical pressure here. It'll be at around 1,000 psi. Okay, we're above 500 psi, or about halfway there. You can see there's still the meniscus there.
It's not even cold anymore. We're getting close.
Okay, right now we're at 68 degrees Fahrenheit. We're waiting to get to around 87 degrees Fahrenheit.
Look how the fluid splashes. We're getting very close to the supercritical state.
Okay, here it goes. Gonna wiggle it a little bit, see what it looks like. Whoa, what is happening? It's like dripping from the top. It's condensing and dripping down. Look at that. It's like a waterfall. That is so weird. That means it's supercritical on the right side, but then it's condensing back into a liquid on the left side, because the right side is where my heat is.
So you can see the supercritical here and then the condensation.
So what's happening is the refractive index of the gas and the liquid are becoming the same. And so you don't see a meniscus, or you don't see the light bend when it goes through the liquid. So then when I shake it, you don't see a real difference between the refractive indices. But you can still see the styrofoam floating on top. Uh-oh. The styrofoam is dipping deeper down in it now. Whoa. It's like disappearing, look. The line's disappearing. The meniscus is just going away, but the styrofoam's staying pretty similar place to where it was.
As we wait for the temperature to get high enough, can you tell me why he's not changing the pressure inside of the flask at all? He's just heating it. And yet we're noticing that along that phase diagram, we're moving diagonally. He's only increasing the temperature, but he must also be increasing the pressure. But he's not doing something directly to change the pressure. How is he increasing the pressure? Why does heating it increase the pressure? Temperature and pressure are directly proportional. So by increasing the temperature, he is having that direct impact on the pressure.
Liquids separate from each other. Okay, it's fully supercritical now.
Does it look more like a liquid or a gas?
Over 1,000 psi now. And the styrofoam is at the bottom.
Looks invisible.
You can still see that it's being heated from the side there, but it's the vessel and move it around.
Now the next cool part is when he starts cooling it again.
With gas above it again. And I think the styrofoam should float once again. Okay, I'm going to put an ice cube on top.
But I don't think I'm going to beat out this ad.
Oh.
Goes invisible. So by increasing the temperature, he also increased the pressure, and brought us all the way into that supercritical state where you could see there was no difference between the solid state, or the liquid state, and the gaseous
there
state.
it is. I saw it starting to float. And it's back on top. Look
You
at
can see that meniscus start to reform.
As soon as it's out of the supercritical phase, then it floats back on top of the meniscus. That is so cool.
This guy is called the Action Lab. He does some really great stuff. I like his videos. I think one thing I especially like about the Action Lab is that he doesn't just report successes. He'll show videos that kind of have failure too, because he forms a hypothesis. He tries to find out what's going to happen, and then he just shows you what happens along the way. All right. We have one last part to our Module 23 on phase changes, and then we're going to spend the rest of today on Module 24. I don't have a worksheet today, which is so sad. Our last day of class, and I have nothing for you to work on. But that's kind of in part because there's no like math-heavy stuff for us to do in Module 24. It's a lot more conceptual based. So I think if we have the time, I'll actually pull up Real Chem, and we'll go through some of those questions on Module 24 together. So the last thing for us to talk about in Module 23 is the Clausius-Clapeyron equation. This equation relates pressure, temperature, and the enthalpy of vaporization. Their equation says that pressure is equal to some constant times E, which is Euler's number. It's a natural constant, raised to the power of the opposite of the heat of vaporization, the enthalpy of vaporization, divided by RT. I'm going to write out some of these variables so that we're all on the same page about what we're saying. P is pressure. A is some constant, not something you need to worry about because we're actually going to work around it. E is Euler's number. That's the E button on your calculator. Delta H of vaporization, of course, the enthalpy of vaporization. R, our gas law constant. And we know there's a lot of different forms of the gas law constant. The one that is most useful here is 8.314 joules per mole Kelvin. And then, of course, T is for our temperature. This equation is not incredibly useful in and of itself. You need to know what that constant A is, and that can differ from chemical to chemical. And all it's helping you solve for is pressure. That means if you know the temperature and you know the heat of vaporization, you can solve for the pressure of your conditions. A lot of times you already know that. There is a more useful form that actually plots these values as the equation of a line. So we rewrite this by taking the natural log of both sides. Ln is the natural log. Not being a math professor, I'm really not well equipped on defining what log is, but it's a mathematical function that says what number you would need to raise a number to in order to get the number that you have. So a lot of times we do log base 10. So like log 100, log base 10 of 100 is 2. 10 to the 2 is 100. So log of 100 is 2. Natural log is what number do I need to raise e to in order to get this number. So that's why it's the natural log, because it's using a natural constant, Euler's constant. E is a natural constant, much like pi is a natural constant. So when we take the natural log of the left-hand side, we also have to take the natural log of the right-hand side. And there's some strange things that happen. That means I take natural log of A, but I also take the natural log of E raised to negative delta H vaporization over RT. Well, what number do I need to raise E to? If I take the natural log of E to something, I basically just cancel out the E. So I get negative enthalpy of vaporization over RT plus the natural log of A. So this is the second form of the equation, but to be fair, this is still not the most useful form. The only thing that is useful about this is that this equals a line. Y equals mx plus b. And it might be a little bit hard to see in that mx portion, what is m and what is x? What is the slope of that equation and what is the x-axis of the equation? And it's typically written as mx is the heat of vaporization times 1 over RT. M, the slope, is the heat of vaporization, opposite the heat of vaporization. And x, the axis, is the inverse of temperature times the gas constant. Cool. So if you go on to take higher level chemistry courses, you will have opportunities to derive this equation and then to plot it. If you create a graph at different pressures and different temperatures, you can solve for the heat of vaporization because it is the slope of all of those data points. But we're not going to take multiple data points and create a graph, so this equation is still not our ending point. Instead, what we want to say is, at any one pressure, the heat of vaporization over RT at that same temperature plus the log of A this must hold true, and then the pressure at any other time and the temperature at any other time must also be true. This should feel a bit reminiscent of our gas laws when we said temperature at some point is equal to pressure at that point times the constant. Temperature at a second point is equal to pressure at a second point times a constant. We can set those equations equal to the constant and equate the instance 1 and instance 2 of pressure and temperature. The constant that we would set these equal to is the natural log. So that would mean taking delta H of vaporization over RT and adding it to both sides of the equation. Because it has that negative sign, we're going to add it. So we now get an equation that says the natural log of P1 plus the heat of vaporization over R times T1 is equal to the natural log of this constant, which is also equal to the natural log of pressure at time 2 times the heat of vaporization over R times the temperature at time 2. Do you see where that got us? We now have two different pressure temperature instances that are set equal to each other by means of this natural log. And so just like our gas laws, we can rearrange this equation in a number of different ways to give us our most useful point. The natural log of P2 over P1 is equal to the heat of vaporization divided by R times 1 over T1 minus 1 over T2. I'm sparing you all a little bit more of the algebra that's involved there. It's actually not just algebra. I don't know. It's not, or I don't know if log functions are just algebra. Is that calculus? No. Is that algebra? Oh. God, I'm glad I'm not in math. This equation is on your useful equations sheet. I want you guys, I didn't bring the equations sheets, but if you have them, I want you to pull them out and look at it. Find that equation. This won't be such a challenge on the Unit 9 to 10 test because you're not going to have gas law problems in the Unit 9 to 10 test. But on the final exam, you will need to decide, I'm given pressure and temperature at 2 different instances. Should I use one of the gas laws or should I use the Clausius-Clapeyron equation? The usefulness of this equation is that if I don't know the heat of vaporization for a specific chemical, I can take the temperature and the pressure of that chemical at 2 different instances, and I can solve for its enthalpy of vaporization. So here is the usefulness. Solve for an unknown heat of vaporization, given that you know P1, P2, T1, and T2. And the math for that is challenging, but not incredibly hard. Plug in P2, plug in P1, divide them on your calculator, take the natural log, take 1 over T1, subtract 1 over T2, multiply that to the other side, multiply R to the other side. You've solved for delta H of vaporization. Doesn't that feel a little bit like the electromagnetic equation that we had, where we could solve for the energy of an electron transition? We had 1 over n final minus 1 over n initial. What's a little bit more challenging is that we can also solve for an unknown pressure or temperature value. If we know the heat of vaporization, and we know the temperature, and we know the pressure at all of the other conditions, we can solve for an unknown temperature or an unknown pressure. And I'd like to actually do one of those problems. Those are more challenging. Oh, shoot, I meant to save that. Well, that's okay. Maybe I'll just rewrite it later. Those are more challenging simply because of the mental math that you have to do. So let's take something kind of meaningful to us. We know the heat of vaporization for water. Is that right? Heat of vaporization for water is positive that is its boiling point. That is the temperature at which the vapor pressure of water is equivalent to the atmospheric pressure, and so the water is able to change phases equally. But that's not its enthalpy of vaporization. That's its boiling point temperature at 1 degree, at 1 atmosphere. Enthalpy of vaporization. I know you've got it on your notes on the page behind us. Positive 44 degrees. Sorry, positive 44 kilojoules per mole. And actually, let's put in that per mole because we saw that the R value has units of moles times Kelvin. and I'll need moles to cancel at some point. At sea level, we experience 1 atmosphere of pressure. But here at elevated levels, we often experience less than 1 atmosphere. Let's say we experience about 0.85 atmospheres. Those of you that were in the lab class this semester, you remember we actually used our actual atmospheric pressure. I have a barometer upstairs, but I didn't check the pressure today. So let me see if I can find that. One of the questions that we were considering the other day is that we know the boiling point at 1 atmosphere. So let's say pressure 1 correlates with T1 at 1 atmosphere. The boiling point is 100 degrees C. So what we want to solve, what I want to work through with you guys today, is can we predict what temperature our water will boil at here at elevated, here at altitude, here at a higher elevation, where we have a lower pressure. And for whatever reason, the National Weather Service doesn't like to use atmospheres. And I don't know if anybody is going to give this to me. 30 inches mercury. I like just make up random units. Let's go inches mercury to atmospheres. I've got 30.21. Yeah, I don't know. That's saying that we're at 1 atmosphere, which I don't agree with. Okay, maybe 0.85 is a bit lower than our actual pressure. So let's say we're at 0.990 atmospheres. This is the information that we have. I'm going to try and keep track of the changes that we make to the equation. Natural log of P2 over P1 equals the heat of vaporization over R times 1 over T1 minus 1 over T2. What do I want to solve for? T2. I have a lot of work to do to get there. Do I want to plug in all of my known values right now? Probably not, because that's going to be a ton of work. So why don't we first try to get T2 by itself? That means multiplying by the heat of, dividing by the heat of vaporization over R on both sides. As you guys know, dividing is the same as multiplying by its reciprocal. So I get R times the natural log of P2 over P1 over enthalpy of vaporization. Are you okay with that? We could have also written that as natural log of P2 over P1 over the enthalpy of vaporization over R, and we would have had a 3-level fraction. So we just multiply by the reciprocal. 1 over T1 minus 1 over T2. Does anybody have their equation sheet? I want to make sure the temperatures are written the correct way. It is. Good. The position that these temperatures are in is crucial. The position these pressures are in is crucial. If you switch them, they change values. All right, now I don't have to write this in parentheses. That can actually look a bit confusing because I'm not multiplying anything over on the right-hand side. I still want to get T2 alone, so I need to subtract 1 over T1 from both sides. So my third form of this equation is R times the natural log of P2 over P1 over the enthalpy of vaporization minus 1 over T1 equals 1 over T2. Sorry, equals negative 1 over T2. Thank you. We can actually go in and change those signs right now if we want to. We can make this negative R times natural log over enthalpy plus 1 over T1 equals positive 1 over T2. And now we've got an issue. We're not solving for T2. We're solving for 1 over T2. So here's what I'm going to do. I'm going to write this in 2 steps, but really you can do it in 1. I'm going to multiply the right-hand side by T2. So T2 cancels. And I'm going to multiply the left-hand side by T2. So in this 4th version, I get T2 times negative R natural log. If you want to wait to copy some of this, I'm going to show one more change. T times negative R natural log over the enthalpy plus 1 over T1 equals 1. Still, I don't have T2 alone, so now I'm going to divide this big monstrosity on both sides. Whew. Even writing it down is annoying. I'm just going to kind of scribble it. It just means that I'm going to have that whole thing now on the denominator. Here's a tip to you. If you need to solve this out during the unit test or during the final exam, you might just want to have your notes handy on the unit test so that you have a version like this that you can just jump to. And on the final exam, you might just want to have on your cheat sheet a version of this equation written in a different form. All right, so equation 5, the final form that I need here, says that temperature at time 2 is equal to 1 over the negative R times the natural log of P2 over P1 divided by, if I'm going to have a triple-decker equation, then I can actually just say delta H vaporization over negative R times the natural log of P2 over P1 plus 1 over T1. No, sorry, that 1 over T1 also needs to be on the bottom. Oh, you know what? I think for that reason, I need to keep enthalpy of vaporization. I'm sorry, it's been a while since I've solved this. I don't want to throw you off, but I think I'm going to keep enthalpy of vaporization on the bottom here. It looks a little silly, but because I have that addition in here, I need to make sure that this entire chunk gets added to this, and that means I can't bring any of it on top just willy-nilly. A mathematician might come in here and tell me that I could write this as delta H over R times natural log plus T1. I might be able to take both of those and flip them, but I don't feel confident on that. Now I start plugging things in. What temperature will water boil at here at elevation? 1 over negative 8.314 joules per mole Kelvin divided by the enthalpy, which is positive 44 kilojoules. Do you see an issue? Will joules cancel with kilojoules? Can we just go in there and change that right now? What does that become? 0.044 joules or 44,000 joules? .44 kilojoules becomes 44,000 joules. Units. Oh, could you imagine not solving this with units? You'd never be able to. On top, I also have natural log of 1 atmosphere, sorry, pressure 2, 0.9 atmospheres divided by pressure 1, 1 atmosphere, which I could have just written as the natural log of 1 atmosphere. Notice how atmospheres cancels inside of there. Logs are a very strange beast. Logs do not obey units. So you can't take the natural log of something that has units. Or if you take the natural log of something, it will no longer have units. And then all of this plus 1 over, do you think I can put it in there as 100 degrees C? Why not? I'm going to need to cancel degrees Kelvin at some point. So that's plus 273.15. I get 373.15 Kelvin. All right, I like to take this a little bit at a time. So let's solve chunks of this and put them back in so that we know we're not missing anything. I'm going to take the natural log of 0.9. On your calculator, this is going to look different, but natural log ln should be written somewhere near log log. Just make sure that you're putting in ln and not log. T2 equals, I got negative 0.105. Okay, you got that too? Let's just go ahead and multiply by negative 8.314. That gives me positive 0.87596. Whoa, I'm not going to write all of them out. Joules per mole Kelvin over 44,000 joules. And if we want to, we can take this 1 over 373.15. We can write it as 0.0026798 Kelvin. No, not Kelvin. 1 over Kelvin. Because I have 1 over that number, which means my unit is 1 over Kelvin. That's actually important because later I'm going to get here. I'm sorry, guys, this is scaring me a little bit because I shouldn't end up with 1 over Kelvin, right? Oh, here I am. This whole thing that I'm starting to solve for is the denominator. So this is all going to be 1 over units of 1 over Kelvin. What is 1 over Kelvin? Kelvin. Units are so fun. Units tell you if you're doing anything weird or illegal. All right, let's take I'm actually just going to go back into my calculator. Take 0.87596 divided by 44,000. T2 equals 1 over, this is such a small number. It's important to note that when I do this multiplication, I made another mistake with my units. This is not joules, this is joules per mole. So I'm able to cancel now joules per mole and joules per mole. I reminded myself back up here that enthalpy is joules per mole. So by dividing these two numbers, I get a very, very small number, 0.0000199, with units of 1 over Kelvin plus 0.0026798 1 over kelvins. What a weird math problem. It's okay, we're doing very important things. Let's see, we're on version 9 of our equation now. We add these two numbers together. Again, I'm going to plug it into my calculator because I don't want them to kind of throw each other off. That's 1 over 0.0026997 1 over kelvins. So now I take 1 divided by that number. When I divide 1 by a very large number, when I take 1 divided by a very small number, do I get a very small number or do I get a very large number? Gets bigger. Divide by a small number, get a bigger number. So I get 370 Kelvin. If we wanted to keep more units, and we can think about rounding later, 370.4 Kelvin. How does that compare to normal boiling point? It's 3 degrees lower. So when you go home tonight and you stick a thermometer in your boiling water before you make pasta, you have a prediction. If your atmosphere is 0.9, if you're just below atmospheric pressure, your water probably won't reach a boiling point at 100 degrees C. Your water will reach a boiling point at about 97 degrees C. Cool. What questions do you have on that math? Is that the hardest part of chemistry? What's the hardest part then? Everything else. For some of you, math comes really easy, and for others of you, math is a different language, and to be fair, it is a different language. That's not even the cleanest I could have done, so I apologize for not making that more clear. There were some really interesting hiccups in there, right? I actually hope that you were able to track those hiccups because it's likely that if it happened to me, it'll happen to you. So let's talk about some of the weird things that we saw again. When I divided by this monstrosity of a piece, I thought about taking certain things and putting them on the numerator, and I decided against it because it meant that I was going to have weird complications with multiplication and addition. And I decided to just leave everything on the denominator. But then I started to plug things in, and I forgot that it was all on the denominator. And that actually started to track. Why? Because of my units. I started looking ahead, and I saw joules per mole would cancel. 1 over Kelvin adds with 1 over Kelvin. I can't add units of Kelvin plus 1 over Kelvin. I can add Kelvin plus Kelvin, 1 over Kelvin plus 1 over Kelvin, but I can't add difference in units with that. So 1 over Kelvin plus 1 over Kelvin, that makes sense, but I didn't want a final temperature in 1 over Kelvin. That means I need 1 over Kelvin to be in the denominator. So I only recognized, did you guys notice that I made that mistake? No, because there's so many other moving parts. It was hard to keep track of the fact that this was all in the denominator. It was the units that saved the day there. Noticing that I was going to get 1 over Kelvin, right. Thank you, 1 over Kelvin, for being in the denominator so that I can take 1 over Kelvin and end up with Kelvin. How far back should I do that? At 5? 5. So in here, you're saying multiply this chunk and this chunk. Okay, that's a mathematician talking to you right now. If you multiply this piece and this piece by delta H vaporization cancels here, delta H vaporization ends up here. Yeah? You guys should hang out with Peter sometime and have him show you how to do that math. I'm going to stick with this. I'm worried that if I make any changes on here, it's only going to make it harder to interpret. But you're onto something. I'll be honest, I love math, but I take it one calculation at a time. And in college, I had a worse calculator than this. I couldn't scroll up to get my previous answers. So every time I had something like the natural log of P2 over P1, I would use a function in my calculator that was called save. I could save it as a variable. And I would just rewrite my equations as this variable is now A. And I would write that in my work when I was doing my problems. A over B plus C. And then I could go in and plug those into my calculator. Be creative. Take risks if you feel confident in them. And if you don't feel confident, go slow. One step at a time. Okay, question for you. What would be easier, solving for 1 over T2 or solving for delta H of vaporization? Do you see now how delta H of vaporization would be a walk in the park, multiply by R, and divide by this temperature thing? So R times P2 over P1 divided by 1 over T1 minus 1 over T2 equals delta H of vaporization. Done. That is a lot simpler algebra, and you don't have to do any of this get T by itself and then get T to be on the other side and swap everything else. That's why I wanted to go through this problem with you. It's pretty much all of the same plugging and chugging, but it's a lot harder algebra to get you set up there. All right. That is all for Module 23. That's all for Unit 9. Our last hour in class is going to be Unit 10. Now that we are here, I'll give you guys a little break, but first, let's talk about those options again. And I think maybe I'll do kind of a little poll, a raising of hands. So the ACS exam next week, Wednesday, 40 questions, 50 minutes. You'll get a blank sheet to do your work on. You'll get an equations sheet from the ACS. You'll get a periodic table from the ACS. No other materials. Your calculator is also allowed. Otherwise, no materials allowed. Option 1, it goes into your homework, and it counts as basically 4 homework assignments. If you do well on the ACS exam, great. That helps your homework 20% category. If you do poorly on it, it's like doing poorly on 4 homework assignments. And for comparison, you've had more than 30 homework assignments this semester. So that's like an eighth of your homework assignments you did poorly on by doing poorly on the ACS exam. Or it goes into the unit test category where it holds about the same weight as a unit test, right? A lot of your unit tests have been more than 40 problems. And whatever your lowest score is on the unit test category, that score gets dropped. So if you do poorly on the ACS exam, that gets dropped. If you do great on the ACS exam, one of your lower unit tests drops. This has the potential to help your score. This will never hurt your score. And for that reason, coming to take this would be only beneficial to you. If you don't come and take it and it goes into your homework, it will definitely hurt you. If you don't come and take it and it goes into your unit test, it can't hurt you. But if you come and take it, and even if you do poorly, all you're doing is getting that extra preparation for the final exam. So that is already an added benefit. A raise of hands for those of you that would like for it to go into the homework category. A raise of hands for those of you that would like it to go into the unit test category. Wow. All right. The ayes have it. I will be adding it to your unit test category and we'll drop the lowest score. Thank you, guys. Take a 5-minute break. Let's be back in here at 5 after so we can do Unit 10 in 1 hour, 50 minutes.
I have a question, Mr. Fly. I was confused just on step 3. We had a negative value for -1 over T2.
Yes.
And I was like lost when you had a negative on the R.
Yeah, I did too many things at once. So I said, I don't want to end up with negative t, so I multiplied both sides by -1. So that went from -1 over t2 to positive 1 over t2.
Oh, so you multiplied this. Okay.
Yeah, and then that went from positive r natural log over enthalpy to negative r natural log over enthalpy, but also minus 1 over t1 to plus 1 over t1.
So this negative is over this whole problem right here, not just the R. I see that's just on the R. But
It's a little confusing because if it's just on the r gets multiplied by the natural log and then divided by the enthalpy. So if the r is negative, that impacts this whole aspect. But technically, what is it called? The transitive property of multiplication. I could have written this as natural log times r, and then that would have just been opposite of the natural log. But also that I could have multiplied it to the bottom. So it technically goes to all of it
okay.
or any of it, and that will have the same impact.
Okay. You said natural log can't hold a negative value?
No. Natural log can't hold units.
Hold units. Okay.
So that was really useful that our atmospheres canceled because otherwise there was no other unit for atmospheres to cancel. But also the natural log can't do functions on units. At least that's my understanding of it. It's a weird thing. So as long as that's a number, and it was just a number, you might have noticed I didn't show it, but that was a negative number. That's because we ended up, we have a number less than E. E is something like 2.34, 2.71. And I wanted to say, what number do I raise E to get 0.9? That's the natural log. What number do I raise E to get 0.9? And I can't raise E to the 1 because that would already be larger than 0.9. So I would raise E to a negative number. So this natural log was some negative number, which multiplied by a negative number, which ended up just giving me that positive number.
Okay, that makes sense now.
Yep.
Appreciate it.
Absolutely. That is, I think, the hardest math problem of the semester. Yeah. I think my first semester teaching this class, I didn't think that equation would actually show up. I didn't think the course lead would make you solve one of those. And then he did. And so the students came to me and they're like, I didn't know how to solve this problem. I was like, yeah, why would you? I didn't show you. So I made it a point now to always solve this problem.
Did you come up with things like the midterms and the finals, or is that something?
And unit tests.
Oh, he does.
Yep.
For like every professor.
There is one professor who has, I mean, I guess the nice way of saying it would be opted not to use the course lead's material. The consensus in our department is that if the course lead makes a decision, everyone that teaches that class needs to follow that decision, unless the course lead allows it as an exception. Some course leads really don't have a lot of preferences. The organic course lead says, go teach the way you want to teach. Make your own exams. You don't have to use mine. Teach the sequence that you want to teach. You don't have to do the same sequence. Other instructors say, teach it exactly the way that I teach it, in the order that I teach it with the exams that I make. And our course lead for this class has said, there's one professor that really doesn't like his way, and he said, okay, fine, do whatever you want to do. So out of the 20 sections of 1210, there's one section that teaches it, or does different tests. I can't though, because it's a lot of work. It's a lot of work to make these tests. I've just got to use the ones that are pre-built. Do you have another question on it, Cole?
I'm trying to figure out how to do the natural log in my calculator.
Oh, let's look. Yeah.
I'm sorry about that.
No, it's okay. So we're looking for ln.
Okay, that's right.
Yep.
And you don't have the log?
No, those are different logs.
Okay.
When you tell your computer log, or your calculator log, you're telling it log base 10. What number do I raise 10 to get this number? When you tell it ln, you're telling it natural log. What number do I raise e to? Did anybody else have a hard time finding the natural log on their calculator? Because Cole's was 2 separate buttons. Mine is the same button. I have to press it twice to get to log. So your calculator probably has its own quirks. Make sure you know how to use it.
Well, the first time this whole time I had log. So it's just
All right, guys. We are on to our final unit. I'll just pat myself on the back a little bit here. It used to be that you had to do the Module 24 checkpoint on RealChem and the Unit 10 checkpoint on RealChem, despite not doing the other modules in Unit 10. And I convinced the course lead to take out the Unit 10 checkpoint because there were questions on there that you weren't learning about. So you have no Unit 10 checkpoint, just the Module 24 checkpoint. You're welcome. Well, just one last thing to do, right? One less thing to do. There is a Module 24 checkpoint.
Oh, there is.
But there is no Unit 10 checkpoint. For instance, we just did Unit 9, which was Modules 22 and 23. So you have to do Module 22 checkpoint, Module 23 checkpoint, Unit 9 checkpoint. This used to be 2 checkpoints, and now it's just 1. So one less assignment. I'm really pulling my weight here. We're talking about solubility. So that means that we're going back to solutions. Solutions, as you remember, are composed of solutes and solvents. How do you distinguish between what is the solute and what is the solvent? The amount. Anything else? A lot of times water is the solvent. There are some really interesting solvents. For instance, RIP the penny. Is that true? The US Mint is no longer making pennies anymore. Pennies are coated with copper on the outside, but the inside of pennies is a zinc-copper mix. And do you know which of those metals is there to a larger amount? Zinc, which makes zinc a solvent and copper a solute. So solvents do not have to be liquids. Solids can have solvents and solutes as well. It's weird. but it's a mixture, it's a solution. And I mean, to be fair, they're melted together, so at that point it feels a lot more like our understanding of solutions. There's another really cool one. I guess I've got two more. Hydrated salts. So you guys might remember early on we talked about chemicals like copper 2-sulfate pentahydrate. That is copper sulfate ionic compounds with water inside of their crystalline structure. So the major constituent there is copper sulfate, and the minor constituent is water. That makes copper sulfate the solvent and water the solute. And then the last one that I want to talk about is the air. The air is a solution. It's not a pure substance. It is mostly nitrogen gas with a bit of oxygen gas and a smidge of everything else. That makes nitrogen gas the solvent and everything else simply a solute. So here are some of the characteristics that these solutions have in common. They are homogeneous. Another way of saying homogeneous is that they're uniform throughout. You don't find one part of a sample that looks different than another part. If that's true, then it's no longer a solution. The physical state aligns with the solvent. For instance, pennies are solids, and the solvent is a solid, so that makes it a solution. The air, nitrogen is gas, oxygen is a gas, so that makes it a solution. If we were to say, for instance, I throw some water into the air, in that instance where my liquid water is sitting in the air, is that a solution? No, because water is not in the same physical state as the air. These are dispersed at a molecular level. So you can zoom in all the way down to the molecular level, and you see that there's not a clumping of solutes here and an absence of solutes somewhere else. Think of it as kind of like diffusion. Everything is spread out and dispersed. A solution also means that the solutes cannot settle out. If the solutes ever fall out of solution, then it's not a solution. They weren't actually dispersed in there. Points 3 and points 4 actually kind of go together. And then lastly, the concentration and the composition can vary throughout. This goes back to being dispersed at a molecular level. If you were to grab 100 molecules from the air, you might find 78 are nitrogen and 20 are oxygen, and then the other 2 vary. Or you might grab 100 molecules and they're all nitrogen. Or you might grab 100 molecules and 50 of them are oxygen and 50 of them are nitrogen. especially if I grabbed the air coming out of your face right now, I'd get a different concentration and composition of CO2 and O2 relative to the air sample that I might grab upstairs on the roof. So that's saying the concentration and the composition can vary. They just need to be homogeneous and they need to be in the same state. Solutions form spontaneously. Do you guys know what spontaneous means? It means what? What does it make you think? Random? Doesn't need a plan. Spontaneously, I spontaneously went to the mall this weekend. Without a catalyst. Actually, that is not wrong. Some reactions, though, are spontaneous, and a catalyst just helps it occur faster. Spontaneous means without external intervention. So a spontaneous process will happen no matter what. It doesn't mean that it's fast. A lot of people think spontaneously means something occurs quickly. Solutions can occur very, very slowly. But if they happen without external intervention, they happen spontaneously. We have a concept called the ideal solution, which is very much like an ideal gas. It obeys some specific rules. I don't have like what I think is a good definition or a meaningful example of it. So I'm going to kind of ignore the ideal solution. I think if you see it on RealChem, you'll make enough sense out of it. But these are actually more important 3 things that impact dissolution. I hate this word, if I'm being honest, dissolution. It sounds like the undoing of a solution, in my opinion. But this means the making of a solution. I guess it's kind of like dissolve. When you dissolve something, you turn it into a solution. So that process is called dissolution, making a solution. We have to consider 3 interactions. Solute to solute interactions, solute to solvent interactions, and solvent to solvent interactions. How well do the solutes hold on to each other? Is it strong or is it weak? How well do the solvent molecules hold on to each other? Is that strong? Is that weak? How well can the solvent interact with the solute molecules? Is that strong or is that weak? And this process of solvent to solvent interactions being interrupted so that the solvent molecules can interact with solute molecules, we call that solvation. So this process of breaking solute, breaking solvent, and combining, replacing them with solute, solvent, solvation. The process of making these intermolecular forces between solvent and solute molecules. You maybe have heard the saying before that like dissolves like. And that is actually the impact here. So for instance, a polar solute dissolves well in a polar solvent. And then the theory would say a nonpolar solute dissolves well in a nonpolar solvent. I actually reject this saying. I don't accept it. It's not true. That's the problem. Like doesn't dissolve like. What I like to say is strong dissolves strong. And I'm talking there specifically about intermolecular forces. Something with strong intermolecular forces, for instance, hydrogen bonding, attracting strong dipole-dipole moments, those will dissolve other compounds that have hydrogen bonding capacity. If you have strong interactions, then they will pull towards each other. For instance, water has hydrogen bonding capacity, and ethanol has hydrogen bonding capacity. So water and ethanol dissolve with each other. They both have strong intermolecular forces, and so they can interact with each other strongly. They're both polar. Specifically, they're both polar with hydrogen bonding. So we can say like dissolves like. Whereas water does not interact with oils. And I'm just going to show kind of a long oil here. It's got 18 of these CH2 groups in between. Oils have very weak intermolecular forces, just van der Waals. Water would rather experience strong hydrogen forces with other water molecules than try to give what little van der Waals forces they have to a long hydrocarbon chain. So when you dump oil into water, what do you find? The oil forms bubbles, they stay on their own, and the water forms bubbles. And we say, oh, that's because like dissolves like. Actually, the oil doesn't like each other that much. They don't have strong interactions. So I say like dissolves like, or strong dissolves strong, and weak is left to weak. Whatever has weak interactions with everything else is just going to get left behind when all of the strong things interact with each other. So the reason that nonpolar things dissolve other nonpolar things is not because they have compatible intermolecular forces. It's because none of them have very strong intermolecular forces at all. So they're just not interacting with anything else. Everything else has been attracted to each other, leaving the things with weak interactions on their own. That's the way that I like to think about it. I think it's a misconception to say like dissolves like. Okay. Are you guys okay with that? Good. You don't have a choice. A few things that kind of come into definitions and impacts of solubility. Around the term saturation. Saturated is a term that describes the maximum amount of a solute that can dissolve in a solvent. This is usually non-zero, but it's not typically there's no maximum number either. Sometimes you reach an amount where no more molecules can dissolve. The other molecules remaining would stay in a different state. Less than that maximum is what we call unsaturated. there could be more solute molecules dissolved in that solution. We haven't reached that maximum number, so we're unsaturated. Surprisingly, you can fit more molecules than that maximum, which gives you supersaturated. This doesn't happen easily. You need some very specific conditions. It's similar to superheating, when you get a liquid hotter than its boiling point, and then all of a sudden it just blows out this huge bubble of gas. It's similar to super freezing, where you get a liquid below its freezing point, and then any disruption will crash all of that liquid into a solid. Supersaturated is when at a given temperature you have more solute dissolved than should be possible. And again, any disturbance will crash out all of that extra solute. They will precipitate out of solution. There's an interesting effect here. I guess what we're going to do is talk about solids and gases and liquids. No, actually, I think now would be a good time to say this. Solids and liquids have increasing saturation or increasing solubility. That is, the saturation maximum increases with increasing temperature. One time I went to Cracker Barrel and I ordered an iced tea. And it was disgusting because it was not sweetened iced tea. It was just unsweetened iced tea. So I took one of their sugar packets and I dumped it into the iced tea and I stirred it around, and the sugar did not dissolve. And I know for a fact that at room temperature, that amount of sugar should dissolve. And I know for a fact that in hot coffee or hot tea, that amount of sugar dissolves very quickly. That's because my iced tea had a low temperature with low solubility. I couldn't dissolve all of that sugar. Instead, I was drinking the sugar from the bottom of the glass using the straw. It wasn't dissolving because at low temps, less sugar could dissolve. The saturation point was lower. Even still, one time I put all of my sugar into my coffee in the morning, came to school, and at the end of the day, I had this ring of sugar sitting at the bottom. Because I hadn't stirred the coffee, I didn't get all of that sugar to interact with all of the hot coffee, and so some of it stayed undissolved. The solubility was high because the temperature was high, but I just wasn't stirring it to make sure that the molecules could disperse enough to be fully saturated. So temperature for solids and liquids, directly proportional with its solubility and its saturation point. But water is different. Gases are different. Gases have decreasing solubility. With increasing temperature. And it's for the exact same reason that solids and liquids have increasing solubility with increasing temperature. Increasing temperature means more kinetic movement. More kinetic movement means those molecules can bump into each other and start dispersing more, spreading out into solution. But with gases, that increasing temperature leads to increasing motion, leads to molecules escaping the solute and flying out from the solution. So I want you to think about your sodas. If you've ever cracked open a cold soda, you hear it go pss, and then it stops. If you crack open a warm soda, it goes pss. More gas is escaping with a warmer soda because that solubility has decreased. the carbon dioxide that has been pushed into your soda, at low temperatures, the carbon dioxide stays dissolved. The gas molecules don't have a lot of energy for motion, and so they can't move past the solute and escape. But at higher energies, those gas molecules have more motion and they can escape from the solution more easily. The same reason the solids and liquids dissolve better with increasing temperature is the same reason that gases dissolve worse with increasing temperature. Better reason, more energy to escape. I think that's really cool. Here's a really big impact on that. So we talked about sodas. That's relatable. But for aquatic life, this is really important. As our climates begin to warm, oxygen becomes less soluble in our rivers and our lakes and our oceans because the gaseous oxygen molecules now have more energy inside the solution and they can escape from the water. The aquatic life that needs oxygen to breathe and to metabolize, they have less oxygen available to them now, so they die off a lot quicker. So with warmer temperatures in our waters, we get less oxygen dissolved, and we get more dead aquatic life. There's another impact on solubility with gases, and it has, I guess actually this won't be a sub-point, this will be a new point. This has more to do with pressure. Gases have increasing solubility with increasing pressure. And it is true that we say temperature and pressure are directly proportional. So with increasing temperature, shouldn't we also see increasing pressure? Yes and no. If I can hold temperature the same and increase the pressure, then I can increase the solubility. And this gives us Henry's law. Henry's law you will actually see on your equations sheet. The concentration of a gas is equal to some constant times the pressure of that gas. This is the final equation on your equations sheet, right before you see the solubility laws. Cg equals Kpg. When they prepare your soda, they keep temperature relatively low, and then they pressurize carbon dioxide gas. With that increased pressure, the carbon dioxide has nowhere to go but into the solution. You're increasing the number of molecules, increasing the pressure. Those molecules are running into each other, and eventually they have nowhere else to go but down into the water. Carbon dioxide, nonpolar. It doesn't interact well with water. It doesn't have strong intermolecular forces that keep it solvated by the water. So the only way I can get a lot of carbon dioxide to go down into water is to force it down into the water with increased pressure. Almost done. I guess I did skip a little bit in my notes. When it comes to liquids dissolving liquids, we actually don't refer to it as solubility. We give it a term called miscibility. Solubility is to be soluble, miscibility is to be miscible. And this is liquids in liquids. We looked earlier and said that water and ethanol are miscible, but oil and water are immiscible. So a bit different from being insoluble, these are immiscible. So that's solutions. Solutions are homogeneous. They're dispersed at a molecular level. They're all in the same phase. Suspensions are different. Suspensions are mixtures that often have heterogeneous characteristics. If you've ever like gone camping maybe and tried to get some drinking water from a river and you see that there's sediment floating around in it, that solid sitting in the liquid is a suspension. Or if you've taken some muddy water, that muddy solid suspended in there makes it a suspension, not a solution. What we can say here is that if you zoom in close enough, different particles are visible. You can look at a part that is just water, and you can look at a part that is clearly a solid. There's no amount of zooming in that you can do to make it look homogeneous. It'll always have these different parts. And these particles in suspensions can settle out. That's the usefulness of taking muddy water. If you let it sit long enough, all of that mud sits to the bottom. Or sandy water, or water with a bunch of sediment in it, all of those particles will settle out, not homogeneous. There's a subset of suspensions, though, that are called colloids. These are still heterogeneous, but they never settle. Maybe never is actually too strong of a word, and we should just say they don't settle. Because to say that they never settle, you can have external forces that start to make them settle out. But on their own, if they're left alone, they won't settle. So I gave this example earlier of a suspension being like muddy water. Can you guys think of a colloid that you know? Milk is a very strange colloid. It doesn't look heterogeneous. But if you zoom in close enough, you can actually find proteins, fats, and water. There are different pieces to it. And of course, milk will spoil, and then it will turn into different layers, but that's not what we're talking about. You can leave milk in your fridge for weeks at a time, and it will stay suspended. You don't get the proteins and the fats settling out of the water solvent. So milk is a colloid. It's heterogeneous, despite looking homogeneous, and it never settles out unless you give it some external intervention. The reason that milk is cloudy is the result of the Tyndall effect. When you shine light at milk or any of these colloids, the light gets scattered off of those bigger molecules, which means you can't see the light go in one side and out the other. The light just gets scattered all around. Can you guys think of something else that experiences the Tyndall effect? Something you see probably every day. A scattering of light that won't let you look through a colloid. The atmosphere? I feel like I can see the mountains most days, but maybe a specific part of the atmosphere? The what? Fogs. Fog and clouds are a great example. Keon, I can't hear you. Oh, I think actually the ozone layer does let light in. The reason the sky is blue is because gas molecules scatter different wavelengths of light to different extents, and blue light scatters the most. So actually, I guess to an effect, yeah, we can say that the atmosphere is a solution, but it scatters light, which is part of that Tyndall effect. Although actually that's named Rayleigh scattering. You're on the right track. Clouds, on the other hand, heterogeneous parts of the atmosphere. And those water molecules scatter light so you can't see through them. You get this white color instead. Clouds are a colloid. There are some other really strange ones, like the inversions that we experience here in Salt Lake City. Inversions are colloids. You can tell that there's a difference in the composition. It's not uniform. That can come from smoke, from dust, pollution, particulate matter from mining, particulate matter from the Great Salt Lake. All of that gets suspended in the atmosphere, and it sits there. And you guys know this. A lot of you have lived here your whole lives, I'm sure. That immersion can sit in the atmosphere for a really long time. What's the only thing that gets rid of the immersion? Rain. And then you get rain droplet-shaped dust marks on your car because the rain pulled it all out of the atmosphere. Sometimes wind, if we get a good windstorm, it'll push it all around and disperse it more. Do you guys remember last year, or maybe it was earlier this year, the inversion lasted so long, it got so thick, it started to settle down and it became an immersion fog. Do you guys remember the fog that came? I think it was a year ago. I ran back into the building one night during that fog, and when I came back out, my lungs were burning because I was breathing in all of that particulate matter that was sitting in the atmosphere and starting to settle. We hadn't gotten rain in a long time, no wind to get it. Some other really interesting colloids, whipped cream. Whipped cream is a colloid where gas sits inside of cream. So you have gas suspended inside of cream. Saint, you had a question?
I was gonna ask, is that why with pollution gets worse, that rain looks dirty?
Yes.
It rains on your car and
Yes. When it rains on your car and it's dirty after, that's because of pollution in the air. That is whatever it might be. Like not fully combusted organic compounds, sand and salt from the Great Salt Lake, dust and particulate matter from the Kennecott mine. All of that stuff sitting in the atmosphere traps water molecules and rains down with them. And then the water evaporates, but the pollution doesn't.
Fires were so bad for us because the wind was pushing all that smoke and stuff that was in the air from those fires over here, and it just got trapped within our mountains. That's why it was so bad.
You could smell it. Do you guys remember smelling the smoke from the California fires? I think there were also some nearby fires that you could smell. All colloids. Okay, one last piece of solubility that I want to talk about with you guys. And that's on soaps and detergents. We say that these compounds, soaps and detergents, are amphiphilic. So that's not hydrophilic, it's not hydrophobic, it's not lipophilic, it's not lipophobic. Amphiphilic is kind of like amphibians. They like both. Amphibians like water and land. Amphiphilic compounds like polar things and non-polar things. So I've given you guys the bond line chain for molecules before, and so I'm going to lean back into that again. Remember that this is just a condensed way of writing carbons and hydrogens in a very long sequence. This portion of the molecule is very nonpolar. So it can interact with things like oil and dirt and grease. All of these things will have intermolecular forces that align with that nonpolar chain. And then we call this its polar head. This is a carboxylate group. It's got ions, which means that it can have ion to dipole interactions with water. So this really likes water molecules because of those strong intermolecular forces. And when they all come together, what they like to do are they form these colloid particles. These colloid particles are called micelles. Micelles are basically the smallest version of cells that you can think of. I know a lot of you guys have biology background. Cells have a phospholipid bilayer, which is pretty much the same structure, a polar head, a very long nonpolar chain, a little bit more complex. And then the bilayer means that two of those molecules stack up against each other, and you get this polar head internal region, polar head external region, nonpolar chain internal region. Well, my cells like to do that. And once again, I'm really abbreviating the carbon chain here. But they will align all of their polar heads at the outside, and they create this sphere with their nonpolar chains pointing inside. And this is where all of the grease and oil and dirt gets trapped, where they have interactions with the nonpolar chain. And then the outside becomes solvated by water. So you can scrub soap on your hands, on your dishes. It'll interact with all of those nonpolar dirt molecules. And then you can rinse it down water, and it'll interact with all of those water molecules. So you get the best of both worlds by doing this. That's all I have for you. I told you there's not a good worksheet for this. It's all just kind of conceptual based stuff. I'm sorry, we ran out of time to do the module checkpoint, but your module checkpoint, I believe, should be the easiest one, this module 24. To be quite honest, the concepts that show up on the unit test and the final exam from this module are small and far between. They really highlight more which of the following will be more soluble in water. And what you're looking for there is what has the strongest interactions with water molecules. That will be the most soluble. I'm going to open up your unit test to start tomorrow, but do you know when your unit test is due? The Sunday night before finals. How many of you have scheduled your final exam? That's a better number than last time. Good. Make sure you get on it because you want to get a 3-hour time frame at the testing center. You have a week and a half to do your unit test. If you do it this weekend, you can come in with questions from that unit test next week during our 2 days of review, our day and a half of review. But you don't have to do it until the Sunday night before finals. Do it early, get it out of the way, get more time to study for your final exam. All right, guys, have a good weekend. I will see you on Monday for our first day of review. Come with questions.